Hey guys, we're going to do this presentation on energy. This is part 3 of our science learning for year 9 and in the lockdown, and we're going to be looking at conservation and dissipation of energy. And the core questions for this lesson: what is energy? What are the units of energy? What are the 8 energy stores? How can energy be transferred? What's the dissipation of energy, and what's the conservation of energy? So if you'd like to have a go at this, pause now, maybe try some of these questions out. Be a good little starting point for you. So what is energy? Well, we've got high energy foods that we eat. It's in a chemical form, and we convert that into movement. It's the movement of kinetic energy. We've also got chemical energy in the form of a battery, which we can convert into that kinetic energy in a different way, like a fan. So energy is being able to move something, quite simply. So the units of energy are in a different form to what we expect. We often read on the back of some food, on food packets and whatnot, what's the unit of energy? It tells us. Kilocalories, calories, joules, what do they all mean? Have a look on the back of your packet of crisps or some food that you've got and see what energy you can find. Here's an example of one. You can see that for every 40-gram portion, which would be the portion probably that they presume you're going to eat, or that packet is of, kilojoules, 805 kilojoules, 195 kilocalories. They're all different. They're different ways of measuring energy. Let's have a look at these units here. So kilojoules, 805 kilojoules in a packet. So you can see there, that's the 40-gram packet that we're doing. How many joules is that? Well, we know that kilojoules, kilo being 1,000, have a look at that. Remember, energy is always measured in joules. Now there are 8 energy stores. Can we guess which this one is? Can we guess what this one is? Can we guess this one, and so on? Have a go. Pause the PowerPoint. Test yourself. Where can we store it? What are the stores? See if you can remember what they are. Write it down, maybe draw it. But pause the PowerPoint and the video, have a go. We've got chemical in the battery. We've got the thermal energy, which is internal energy in the heat, in the cup of tea. We've got magnetic energy that's stored. We've got gravitational potential energy that's stored the higher we go away from the pull of gravity on the Earth. We've got electrostatic in the form of, well, lightning that we can see there. We've got the kinetic energy store that we talked about earlier. We've got the more complex nuclear energy store. And we've got the elastic potential energy store. And these are all energy stores that you can see now. Have a little description. Now see what you got right, see what you can remember, see whether you know what they are. Look at the examples, have a look through this. Pause on this video point, see whether you got, check yourself, see if you know what they mean. Just having a brief run through quickly. Magnetic, when repelling poles have been pushed closer together, or when attracting poles have been pulled further apart. There's an energy store there. When we have the internal energy, we have the kinetic and potential energy of the particles. Most obviously the vibrations that we know when we look at the different changes in state and how gas has more energy than solid. And we can see that the hotter some energies are, the more internal energy they have and the more vibrations that go on. We've got the chemical bonds, the bonds between those molecules is where that energy is stored there. The kinetic is the energy of that moving object. We talked about that earlier as well with that runner and how we converted the chemical into the kinetic. Electrostatic, the energy stored when repelling charges have been moved closer together or when attracting charges have been pulled further apart. Very similar to the magnetic energy there, just in a static form. And we have elastic potential, the energy stored when an object is stretched or squashed. So when you pull like maybe a rubber band or something, you're holding it into position, you're holding an elastic potential energy stored there. And you have the gravitational potential, the energy at the object of height, like I spoke earlier about, away from the pull of the gravity of the Earth. And then we have the nuclear energy, the energy that's stored in the nucleus of the atom, often used in nuclear power. So we've talked about the energy stores, and now I'd like to look at how energy can be transferred. I did mention a few a few examples of transferring energy a minute ago. So let's have a look at some of these. This one goes from one form of energy into three forms of energy. Pause the video, have a go, see if you can answer what each arrow is. Tell me what each arrow is. Where does it come from? How is it transferred? And what is it transferred into? So we know that there's a battery in there, and that's a chemical store. And that chemical store comes through electrically into the motor. The motor then turns the mechanical movement into a kinetic energy. There is some heat generated with the friction, which is the thermal, and there's some radiation outside where the movement of molecules causes that sound transfer from that motor. So energy can be transferred from one store to another in many different ways: mechanically, electrically, heating, and radiation. And there's the four that we've given examples of there. Now, usually we only want the kinetic energy in the movement of air. That's the useful energy that we want from that fan, in this fan example. But we don't need the heat, we don't need the sound. So they're considered wasted energy. So let's describe this energy transfer. Let's look at a bouncing ball. We've got a bouncing ball, we've got a basketball. There's gravitational store as the basketball gets higher, and it depletes as it goes lower. The thermal store is filled, and the energy is transferred mechanically from that push. Let's have a look at that in a diagram. Let's see what that looks like in a diagram. Gravitational potential energy, GPE we call it sometimes. Mechanical work to kinetic energy, mechanical work to internal energy. So there's quite a transfer going on there. When the ball's up high, you have the potential, and when the ball is moving, you have the kinetic. When you hit the ground, you've got the internal energy, that movement of the molecules inside, that vibration, that's causing the heat. And there is heat when you bounce the ball on the floor. Very small, but there is. Okay, let's look at another example of this. Energy can remain in store for millions of years, or sometimes just a second, or even fractions of a second. There's energy going on all over the place, all the time. Loads of energy changes, transfers, all sorts going on. Look at another example here. We've got a swinging boat, something that you probably see at a fair, and you've got a maximum kinetic energy in the middle when it's flowing at its fastest, and then it slows down as it goes up, but it gains its gravitational potential, and then it drops again. And it drops again, and the kinetic energy increases at the minimal gravitational potential because it's at its lowest point, and then back up to the highest point of its swing again. And you can see that here. Gravitational to kinetic, and back to gravitational. Now it will eventually come to a stop if it wasn't mechanically assisted. And that's because obviously there are some areas of wasted energy like the heat and the sound. You can hear the movement of the ball bearings moving around, on the pivot and things like that. There is a link there that you can follow. I'll try and include that in your show my homework, so that you can click that link if you wish to follow that and have a look at that. So let's look at comparisons here. We've got stores and transfers. Pause the video, make a few notes, and see what you can remember. See what what you know of each one. It's just worth having a look at this. This is going over what I've just spoken about. And then we could look at energy changes in a system. Let's look at energy changes in a system. So we've got the system bringing water to a boil on a camping stove. As the fuel burns, the chemical energy store and the fuel decreases. Internal energy store of the water increases. There again, there's that transfer of energy going on. The temperature of water increases as the bubbles form the kinetic energy store and the water increases. So again, an energy transfer. An object thrown upwards. You throw a tennis ball upwards. The ball leaves your hand. Store of kinetic. Highest point, greatest store of gravitational. As you're about to catch it, it has a full store of kinetic energy. It's dissipated then into another transfer. Heat on your hand when it hurts your hand if you throw a ball that hard or that high. So we talked about dissipation of energy earlier. What is dissipation? Well, no system is perfect. Right? Nothing can be perfect. If not, it would just continue to work and we wouldn't need to provide energy for it. We'd have cars that never needed fuel and so on and so on. So there is a change in system and some of that energy is dissipated. We could use this example here. So like the mechanical system of a bike. When two surfaces rub together, you've got friction. And when you've got friction, you've got that wasted energy, and there's a surface on the road that wastes the energy in the cycling kinetic movement. You can add a lubricant. I wouldn't want to add a lubricant to my tyre, you'd slip off the bike. But you could help in the chain situation, so you could add lubricant to the chain, so there's less friction in the chain, so all of that kinetic energy is being transferred, or as much as possible. It won't be all of it, but it'll be as much as possible. You need a bit of friction on the road. You need some. You'll fall off. But there is a couple of examples of where dissipation occurs. Now we have the law of conservation. Now we must remember that energy, we can't make energy on the earth. We can't just create it. So let's look at what that is. We get the energy from the sun. It comes in the radiation form onto the earth, and we then do something with it. More than often, it's depends, like we said, whether it's over millions of years or whether it's immediately. So it kind of goes through that infrared radiation, through the space, and it hits the earth. Remember, there's no air molecules in space to heat up and move around, so it's quite an efficient transfer of radiation. This means that all the energy in the universe was present at the Big Bang and will still be around to the very end of time, because energy can't be lost and it can't be created. It's always there. It's just being stored in a different way. So let's look at how energy is conserved. Let's look at the skydiver. This skydiver looks happy. I don't know whether I'd be happy jumping out of a plane, but there you go. When the skydiver jumps out of a plane, she begins to lose gravitational potential energy and increases kinetic energy. The speed increases. There we go again. We're looking at another diagram of how it works. Gravitational potential, the mechanical work goes in, and kinetic energy comes out. There is an internal energy too. So the total gravitational potential energy equals the kinetic energy plus the internal energy. Quite a simple, what would you say, a formula or an example for you to remember. I'd probably pause the video now and write that down, make a note of it. It's quite an interesting one. You might get a question on that later on. And we look at the law of conservation again. So I've talked a bit about the law. I haven't given you a specific, but here it is specifically. Cannot be created or destroyed, but the change from one form to another. Now, I would pause there and make a note of that. Very important law of conservation of energy. So let's look at some questions. What energy transfers in boiling a kettle? What energy transfers in lighting a candle? What energy transfers, but not all useful, and how does that come in? Hang on a minute. When an energy transfer occurs, not all of it is useful. What is the name for this energy? Sorry. So what is the name for the energy that's not useful? Got a bit of a tangle there. Pause your video, have a go at these questions, see what you've remembered from what I've said. Here we go with the answers. 3, 2, 1. So the chemical store is depleted and the thermal store of the kinetic are filled. It's transferred electrically. Let's look at the candle. Chemical store is depleted and the thermal store is filled. The energy is transferred by radiation and heating. And finally, the answer, the third one, we call that wasted energy. And the wasted energy in our example of, it's not Henry, but it's James, I think, the Hoover. It's noise. It's actually noise, the wasted energy. So just to conclude today, you will have some attachments. Feel free to ask Ms. Soper any questions about these this week. There are some questions and attachments. I'll put them in PDF and in Word document for you to support you on Show My Homework. Best of luck. Have a go and be ready for our lesson on the Friday. All the best.